As chromatographers, we don't get too excited anymore about a presentation at a conference on resolving two enantiomers from a racemic mixture. SFC has been associated with chiral resolution for quite some time, and these kind of presentations are routine. What I want to talk about today is less routine. Very recently, we've noticed that in an attempt to introduce greater molecular complexity into the molecules that are of interest to medicinal chemists, those chemists have been working with chiral molecules that contain multiple stereocenters. 2 stereocenters gives us 4 isomers, 3 gives us 8, 4 gives us 16, and so forth. And the resolution of these isomers and their capture in high yield is quite a challenge, and what I'd like to talk about today is that challenge. Molecular complexity is associated with high target specificity, and that means reduced toxicity. More promiscuous molecules tend to have greater off-target effects, and that's something we want to reduce. One of the things that is associated with molecular complexity is the fraction of chiral atoms present in a molecule. And introducing more chiral atoms gives us a greater degree of complexity and three-dimensionality. In working with several different databases of drugs and molecules that have been tested as potential drug molecules, one of the things that we notice is that virtually all of these have no chiral centers at all, and only a few have 1 or 2 or 3 chiral centers. So that's something that we're seeing an increasing amount of work coming into our laboratory, requests for resolution of 4, 8, or even 16 isomers. Again, we'd like to produce these all in high yield and at good enantiomer purity. So how do we do that? We all know that with one stereocenter, this process is fairly simple, particularly if you've got a racemic mixture where the enantiomer pair is present in a 1-to-1 ratio. The isomer pair is usually fairly obvious as you screen different chiral stationary phases, and focusing in on resolving that single pair and capturing the peaks from that single pair is a fairly straightforward task. With 2 stereocenters, it begins to get more difficult. One of the things we have to remember is that the yield of the enantiomer pairs in these molecules is not always equal. So what we may see is a large pair of enantiomers and a smaller pair of enantiomers. At that point, things like chemical impurities begin to make our separation even more confusing. 3 or more stereocenters, it just begins to multiply exponentially. Here is an example of a 3 stereocenter separation where across this narrow range we see 4 peaks. Now this is an achiral separation on a gradient UPLC system. And what we're doing here is we're leveraging the very high degree of resolving power and the tight band shape and the high reproducibility in UPLC to resolve not the individual isomers, but the pairs of enantiomers within this mixture. And again, as I said, they aren't in equal yield. We see a big pair, we see a medium-sized pair, and we see 2 smaller pairs. The peak at 1.32 minutes is an impurity. I'm going to focus mostly on 3 stereocenter compounds because they represent a fairly complex problem without becoming too far in the weeds. But let's start with a 2 stereocenter sample where we get 2 pairs of diastereomers, or 2 pairs of enantiomers that are diastereomeric to one another. This is again achiral UPLC, and what we've resolved here are 2 peaks that are present in a roughly 75 to 25% ratio. Now, this ratio is important. What this tells us is what we should be looking for in the chiral separation, because once you separate these into their pairs of enantiomers, and the enantiomers are generally present at 50-50 concentration, we should see 2 peaks that are roughly 37% of the total area and 2 peaks that are roughly 12% each of the total area. When we screen using gradient SFC, uh, for chiral stationary phase interaction, you see a variety of conditions that have some phase interaction, but not everything we'd like to see. I'll point out right away that methods 5 and 6, whatever they are here, do produce the peak ratios that we'd expect to see from a full separation of all 4 of the isomers. And we may be able to scale one or either one really of these 2 methods up to give us a one-stage separation, clean separation into all 4 individual isomers that we want. It's not always going to be this simple.